All right, so we're talking about this very simple problem first. We want to maximize a profit based on a lumber company deciding how many board feet of two types of lumber that they want to process. So the profit function is given by $120 of profit for every 1,000 board feet of finished grade lumber, which is being denoted by X, and $100 for each 1,000 board feet of construction grade lumber, which is denoted by Y. And we want to maximize profit relative to these two constraints. 2x plus 5y is less than or equal to 8. 8 is the number of hours that the company has available to basically cut wood and saw the wood into these lumber boards that they want to process. And then they have 15 hours available to plane them or smooth them. So again, in this very simple example, this feasible set, these two inequalities, one of them actually is redundant and doesn't actually come into the decision at all. That's the second one. So when we graph the feasible set, we really just get a triangle, which we see here. And the line I have here is our objective function. And we've seen that the solution is profit of $480 occurs when we decide to choose to make 4,000 board feet of the finished grade lumber and 0 board feet of the construction grade lumber. And again, remember how this works. This line, the slope of this line is tied to the numbers 120 and 100. Those are basically just, this equation that is our profit is really just a linear equation. Once I put in a number for profit, that gives me a line, and we're trying to find the line that has that slope and is basically as high as possible and still touching our feasible region to help us identify the optimal decision. So again, if I move the profit, I want to make more profit, that's not feasible because the line is no longer meeting any of the feasible decisions that we could make based on the constraints. So we have to accept a profit of 480 because that's the highest amount of profit that will actually lead to a decision that's feasible. Again, in real life, if you wanted to be less optimal, you could always decide something else. You could accept less profit and have more variety of decisions that you could make. But since we want the optimal profit or maximum profit, that's why our solution is here. So the idea of sensitivity analysis is the company has its decision. They're going to focus on only making one kind of product. Now, in general, you could think of a company who has potential to make hundreds of different products, but it may be profitable to focus on only 20 or 30 of those products. But they want to make sure that if they decide to only make 20 or 30 of those 100 products, that's going to maintain profitability for an extended period of time. So we're starting very simple. So these numbers that come from the profit of each of these products that we're going to make, these are based on lots of things. There's demand from their customers, how much of those products actually other companies want to buy from them, and there are material costs and labor costs. All of those go into determining these numbers 120 and 100. So as the market changes, these numbers could change. So for example, it could happen that the finished grade lumber becomes more profitable because maybe more companies want to buy it, and perhaps the cost of getting access to that lumber goes down. In that case, the profitability of that product goes up. But if that profitability goes up, that changes the slope of our objective function. So let's just say it increased from 120 to, let's say, 150. So it's now profitable to basically make $150 profit instead because of how the market has changed. Well, if that's the case, we have to redo our linear programming problem. And all that's doing is telling us that we can actually make more profit. So we move our line and it to the optimal decision, and we notice that it's the same optimal decision. We still want to make only finished grade lumber, but now because of how the market has changed, we can make $600 profit with the same decision. Now this can go either way. The finished grade lumber could become less profitable. It could go down, say it goes down to 80. In that case, we'd have to rework our problem. We bring our line down and see where it first touches our feasible region, and it's the same decision again. So lots of changes in the finished grade lumber and how its profitability is could lead to the same decision. The only thing that's changing is how much profit we're actually making. In this case, we're going to have less profit, but it's still the best decision for the company. So again, the idea of sensitivity analysis is to, once you have a decision, identify how much these numbers can change so that you will still have the same decision. If the range of numbers of these numbers that we're going to be putting into our objective function, if their range is very large compared to the profit, for example, then what that's saying is that in all likelihood, it's going to take a long period of time before a new decision has to be made. And that's, in a sense, that's good. That means the company can basically plan to automate things, save a lot of money on labor costs, and know that they're going to maintain profits for an extended period of time. But if the market is very volatile and the numbers are going to change erratically over short periods of time, then long-term planning is a little more difficult. So what we want to see is how these numbers can change to affect when the decision will have to be changed. So let's go back to the original problem here, where we had 120 and 100, our profit of 480, with our decision of 4,000 board feet of finished grade lumber to process, and then 0 board feet of the construction grade lumber. Now, what could make us change our decision? Well, if the finished grade lumber loses profitability by a lot or enough, it may become more advantageous to start producing construction grade lumber. Or if the construction grade lumber becomes more profitable, it may be better to choose to make a combination of construction grade and finished grade lumber. So let's look at what happens when we move or change the value of the profit for the construction grade lumber. As it goes up or down, let's make it go up. Notice the slope of the line is changing, but it's not actually moving away from our decision. And the reason for that is because this variable doesn't come into play in this decision. Remember, this decision is let y be 0, so it's not really affecting anything. So it can change quite a bit, and our decision is still the same. But if it changes enough, if this profit per 1,000 board feet of construction grade lumber increases enough, the line will eventually meet an edge of our feasible set. And when it does that, that's telling us that we have infinitely many choices of how we could choose to produce these two products and still have the same profit of 480. Basically, any decision on the top edge of this triangle now would be equally profitable. So we could have all finished grade, or we could even do all construction grade and no finished grade, or some combination of the two. Now, if the profitability of the construction grade lumber increased even more, now our slope of our line is such that it's actually cutting through our feasible set, so we'd have to raise our profits, and then we see that we would only want to produce construction grade lumber now. Because it's so much more profitable, a new decision is now valid to make profits. So the idea is, in these two variable problems, it's very simple. Just kind of playing around with the slope of this line to see how much it can change before we have to make a new decision.